Okay, this is trigonometry topic 4, solving right triangles, part 2. So we're going to look at some applications of solving right triangles. So hopefully you remember solving right triangles and how to find all the different angles, all the different sides, especially using inverse functions, inverse trig functions that is. And let's talk about a couple of the applications we're going to use. The first application we're going to talk about is the area of non-right triangles. And you might be saying, well, wait a minute, I thought this was about right triangles. We're actually going to use right triangles to help us find the area of non-right triangles. The second application we're going to use is angles of elevation and angles of depression. So we got to do a quick review about that. And use E for elevation, D for depression. And the third thing we're going to talk about is bearings. So when you're talking about ships or airplanes, they navigate by bearings, which is called how they find their direction that they're traveling is by bearings. And it uses degrees, and it uses direction and angles and all that kind of stuff. So we're going to talk about that as well. So let's first talk about this triangle. So notice that this is the triangle here. And notice it's a non-right triangle. Okay, and the area of a non-right triangle, the area of any triangle, you should probably learn back in middle school, is 1/2 times the base times the height. Okay? So if we look at this triangle, and we're going to try to use this formula, we have that the 1/2 times the base is letter B at the bottom. B is all the way from A to C. That's the base B times the height. But the problem is usually the height is something we don't know. So we want to try to find that height in terms of the actual sides of the triangle and the angles, not the actual height. So let's emphasize the right triangle that I have shown here, which is created by dropping that height straight down. So we know that according to angle C, H is the opposite side and A is the hypotenuse. B is not the adjacent. Okay, the adjacent would be just this part right here, that I have highlighted in pink, and the entire B is all the way from A to C. So this adjacent side is part of B, but not all of it. I don't even know what part of it, so that's why I can't really use B. And I know that sine of angle C equals the height H divided by the hypotenuse A, or opposite over hypotenuse. So if I'm solving this for H, I got to multiply both sides by A, and I get sine, or A times sine of C equals that height. So when I come back to my formula here, I could replace the height H with A times the sine of C. And what we realize here is that the formula for the area of any triangle is 1/2 a side times the angle in between. So it doesn't even matter what angle you're talking about, but you have to use the two sides that create that angle. So another formula I could use for area of this particular triangle would be 1/2 times, well, let's say I was looking at angle B. So it would be the two sides that create it, C times A, those are the two sides that create angle B, times sine of angle B. Or there's one more formula. I could look at angle A and do 1/2 times the two sides that create angle A, C times B, times sine of angle A. So I know that seems a little bit confusing, and don't let three formulas throw you off. Just remember, it's sine of an angle times the two sides that create it times 1/2. So it's 1/2 times the two sides times the angle in between. So let's look at an example here so that this makes sense to you. Here's an example of a non-right triangle, okay? And I know an angle, 82 degrees, and I know the two sides that create it. So area is very easy to find here. It'd be 1/2 times 8 times 13 times sine of 82 degrees. So you have to be able to know the two sides that create that angle, and then the formula is that easy. So it'd be it'd be 0.5, that's the half, times 8 times 13 times sine of 82 degrees. Make sure you're in degree mode on your calculator, and you get that the area of this triangle is 51.49 square units, or units squared. There were no units given, so I would just say units squared. Okay? Now we can also use this to figure out parallelograms, because remember, a parallelogram, right? This is 7, that means this is 7. Base is 15, that means this is 15. This is 65, that means this is 65. These are all things about a parallelogram that you should remember. But if I cut that parallelogram in half, I create two identical triangles, 1 and 2. So if I find the area of one of them, I can just double it to find the entire area. And look what I have here. I have an angle and the two sides that create that angle. So the area of that triangle 1 right there is 1/2 times 7 times 15 times sine of 65 degrees. So on my calculator, 0.5 times 7 times 15 times sine of 65 degrees. And I get that the area of triangle 1 right there is 47.58 units squared. And if I just double that, because that would be the area of angle or triangle 2 as well. So the total area of the entire parallelogram would be 95. And again, I'm just doubling this, 95.16 units squared. So really easy formula. It's all based on an angle and the two sides that create it. Okay, so let's slide over and let's start talking about angles of depression and angles of elevation. Okay, angle of elevation, angle of depression is all based on your horizontal line of sight from your eyes. So if my eye level is right here and I'm looking straight across, the angle, that's really nice and straight across, huh? The angle of elevation is the angle from your horizontal line of sight up to the angle that your eyes are looking at that object that's above you. Angle of depression would be looking straight across and then looking at the angle down to that object that you're looking below you. So elevation is looking up, angles of depression is looking down. But that angle is all calculated from the horizontal line of sight. Okay, so let's read this example and try to solve this one. You are standing 20 feet away from a tree. You measure the angle of elevation to be 38 degrees. How tall is the tree? So the 38 degrees that we're talking about is from my straight line of sight over and then 38 degrees up. Now the interesting thing about this problem is this is the entire height of my tree right here. This is my entire tree from the ground all the way to the top of the tree. However, I have to take into account my 5 feet that my eyes are above the ground. So for my particular self here, I'm 5 feet above the ground. So let's look at this right triangle. And all I got to do is once I find T right here, I have to add on the 5 feet that my eyes were above the level, above ground level. So let's see here. In this triangle right here, T would represent the opposite side. 20 right here would represent the adjacent side. The hypotenuse right here is not given, nor was it asked for. So I'm going to use tangent, because tangent is who uses opposite and adjacent. So tangent of 38 degrees equals the opposite side T divided by the adjacent 20. So multiply both sides by 20, and on my calculator I'm going to do 20 times tangent of 38 degrees, and I get 15. I get that T there is 15.63. But you got to remember that that is the distance from my eyesight, 5 feet above the ground, to the top of the tree. So I have to add on the additional 5 to that value to compensate for my eyesight, or my eyes being 5 feet off the ground, and I get that the total height of the tree is 20.63 feet. Okay, so hopefully that was pretty easy, understanding angles of elevation there. Here's a problem that utilizes angles of depression. You're standing on top of a building looking at a park in the distance. The angle of depression is 53 degrees. If the building you are standing on is 100 feet tall, how far away is the park? Does your height matter? So let's first pretend that my height doesn't matter. And I'm talking about the angle of depression being 53 degrees from the top of the building. So here's the top horizontal line of the building. 53 degree angle of depression means depression going down. So, height of the building is 100 feet tall. I'm looking for the distance from the bottom of the building to the park. And A is the, a lot of people will use 53 here, but you got to remember 53 is the angle of depression. So A would actually be 90 minus the 53. So A would actually be 37 degrees. So I'm talking about this right triangle right here. Here's that right triangle. I need to be using the 37 degrees. D is the opposite, 100 is the adjacent. So tangent of 37 degrees equals the opposite D divided by the 100 adjacent, multiply by 100 on each side. So tangent of 100 times tangent of 37 degrees is 75. This would be D is 75.36 feet. Now here's the problem. My height does matter. Yes, it certainly does matter, because actually here's my eyesight right here coming straight across. The 53 degrees is from my eyesight straight down. And that means that my eyes are not 100 feet off the ground like I was assuming the problem. My eyes would actually be, well, if my eyes are 5 feet off, from my feet to my eyes, 5 feet, then this entire distance would be 105, not 100. So I got to go back to this problem and change this all to 105, because my eyesight does matter. Not my eyesight matters, well, I guess it matters, but the actual height of my eyes matters, or my height in the problem matters. So if I do 105 times tangent of the 37 degrees, I get a total distance that is correct because of my height coming into impact, I guess 79.12 feet. Okay, so that would be the height, or I'm sorry, not the height, the distance away from the building to the park. All right. Let's shift gears to bearings real quick, and bearings deal with how ships navigate and how planes navigate, and they all are based on a compass here, where we got north, south, west, and east. And the first coordinate you give is always north or south. So for this particular drawing here, the angle I've drawn is north. It's not down here in the south, and it's say 70 degrees east. So what this means is you are north 70 degrees from north to the east. That's how you read this. You're 70 degrees from north to the east. This picture right here would be north 70 degrees west, because I'm north and then 70 degrees west from that value. Okay? So let's kind of figure out, how would I draw. Let's make a drawing for south 40 degrees west. Okay, so you start off with south, and you're 40 degrees to the west. So this would be my 40 degrees right there. So start off south, 40 degrees to the west. For it's south, 40 degrees east would be going this way. So south, 40 degrees to the east. Okay, so that's kind of how bearings work. So it's a real quick lesson on bearings. So hopefully that makes sense. You never start off with east or west. You always start off with north or south. That always comes first. So let's look at a problem here. A ship travels on a north 50 degrees east course. The ship travels until it is due north of a port which is 10 nautical miles due east of the port from which the ship originated. How far did the ship travel? Okay, well, sometimes just getting your bearings straight, no pun intended there, is the hardest part about these problems. Okay, so start off with your home port. Okay, and create kind of a dotted line here for the compass, right? So here's the port I'm leaving from, and it says I'm leaving at a course of north 50 degrees to the east. So here I go. So this right here would be the 50 degrees that I traveled. So north 50 degrees to the east. And I'm going to travel until the ship travels until it is due north of a port which is 10 nautical miles due east of the port from which it originated. So here's the port from which I originated, right here at the center. And it says it was 10 nautical miles due east of that port. So here I am, and I'm going to 10 nautical miles, and due east obviously means straight east. So the ship travels until it is due north of a port which is 10 nautical miles due east. So here's the new port, and here I am due north of that port. So I'm straight north of this port right here, which is 10 nautical miles due north or due east from the port which I left. So a little bit confusing. Here's the port I left. Here's another port right here that is 10 nautical miles due east, and then I stop my current path once I am straight north of that point. So of course, the whole point is you're creating a 90-degree triangle here, okay? And it wants me to know how far has the ship traveled. So that would be this distance right here. How far has the ship traveled? We'll call that x, okay? So the first thing I realize is that I have 10 nautical miles down here. I could use that to my advantage, but I need to know the angle inside of the right triangle. 50 degrees is not that angle inside, which of course that would be 40 degrees. So I'm not using the 50, but I needed the 50 to know that this is 40 degrees. So again, I'm going to use cosine here, because cosine of 40 degrees equals the adjacent 10 divided by the hypotenuse x. So I'm going to multiply both sides by x. I get x times the cosine of 40 degrees equals 10. Cosine of 40 degrees is just a number that I could divide by. And I get that x equals 10 divided by cosine of 40 degrees on my calculator is 13.05. So it's 13.05 nautical miles. You don't have to worry about how far a nautical mile is, but you just answer it in nautical miles. So hopefully that question made some sense. It was a little bit of a tricky one. It wasn't the easiest problem, but hopefully it made sense in terms of how to solve that. All right, before we move on, I just want to really emphasize again that you have to read the problem. You know, I mean, these problems can be a little bit tough, okay? Let me kind of give you another one here. Let's say that we're a ship that we leave port right here, and we travel a destination, or we travel at a bearing of, let's see here, south 30 degrees east. Okay, so we start going south 30 degrees to the east. Okay, so that would be this way right here. Here's that 30 degrees. Okay, and let's say that I travel in that direction for a while. Okay, and I want to know how far I've traveled. okay? And like the previous question, there's a whole lot of different types of questions that you could ask, but here I go. 30 miles or 30 degrees southeast, okay? Then at that point, I traveled for a while, I stop, and I'm going to go due east, straight due east, okay? And then I'm going to stop at some port right here. So here's where I stop. And I want to find how far am I away from that port. So how far away is that new port away from the original one that I left, okay? So this could be a little bit tough. I have to give you a little bit more information. Let's say that I knew I traveled south 30 degrees east. I knew that I traveled that for 15 nautical miles. Okay, so let's see here. I'm going to drop this down, drop this over, and let's also say that I know that I traveled due east, okay, for 6 nautical miles. This picture is definitely not drawn to scale. So again, I want to know how far I was total away here. Okay, so the first thing I have to find is, well, I can't use Pythagorean's theorem yet because this is not a right triangle, but overall it is a right triangle. So I need to find this green distance right here, and I could use the fact that this is 30 degrees, the hypotenuse is 15, and I'm looking for this side right here. I'll call it x right now. So that, let's see here, that is going to have to be using sine, so sine of 30 degrees equals the opposite x divided by the hypotenuse 15 times by 15 times by 15. So 15 times sine of 30 degrees is exactly 7.5. So x is exactly 7.5 nautical miles. So this distance down here is 7.5 nautical miles. So now I also am going to need so now I know this total distance down here, this huge distance down here is going to be 13.5 nautical miles. And now I also got to find this distance over here. So once again, I can come back to this original triangle that I drew right here. And I know that, let's see, this time I'm going to have to use tangent. Tangent of 30 degrees equals the, oh no, I don't want to, okay, I made a mistake. I guess I could use the 7.5 as long as I'm 100% knowing it's true, especially because it ended up being exact. But I'd rather actually use cosine of 30 degrees equals the opposite or the adjacent side right here divided by the hypotenuse 15. So I can find that side as well. So again, multiplying 15 times cosine of 30 degrees, I get 12.99. So that's this side right here is 12.99. So now that I know this side right here, 12.99, this whole side down here, 13.5, I could actually use Pythagorean theorem. Now I know I'm going against the rule that I kind of said in class about using rounded values, but there's really no other way to do it. So I know that 12.99 squared plus 13.5 squared equals this total distance from port to port squared. So I get 12.99 squared plus 13.5 squared equals 350.99, and I'm going to take the square root of that, 350.9901 actually, and I get that total distance right there is 18.73 nautical miles. So another application. I know it was a little trickier one, I apologize, but I'm just trying to prepare you for problems that you're going to see in class. Okay, let's come back to the last problem of the day real quick. It's actually a much easier problem, the wheelchair ramp. Okay, you were building a ramp so that people in wheelchairs can access the building. If the ramp must be a height of 8 feet and the angle of the ramp must be 5 degrees, how long must the actual ramp be? So how long from the ground all the way to the top is that ramp? So let's see here. Based on 5 degrees, the 8 is the opposite. X is the hypotenuse. So that's going to be sine. So sine of 5 degrees equals the opposite, 8, divided by the hypotenuse, x. So I'm going to multiply both sides by x. And I get x times sine of 5 degrees equals 8. I'm going to divide by sine of 5 because that is just a number. I can use my calculator to find it. So using my calculator, 8 divided by sine of 5 is 91.7. Let's see here. 91.79 feet. And that is the value there. So anyway, I know we went through a lot of examples there, but hopefully most of them made sense. I know that bearing stuff can be a little bit weird. We just got to practice it and practice it and practice it, and you will become much, much better. All right, see you guys in class.